In the last video, we priced a call option and a put option using this one-step binomial tree pricing idea. And that hinges on setting up a portfolio of buy the option and short some of the stock. Pick the delta so that you hedge both cases of the future, and then use an arbitrage argument to figure out what this portfolio should be worth now. We're going to do the same thing, but I want to do this very much in general. So I want it to work for any option. So let's change this then. And it's going to be price, let's just change this to option. So this should work for whatever. Oh yeah, price and option. And with an exercise price, we'll just have an exercise price. We're not going to specify that. We're not going to say next month. We're just going to do a time step of dt. So we're trying to keep everything very general. If dt is a month, if the time step's a month, then dt is a 12. If the time step is a day, then dt is, the book uses 1 over 252 because there's 252 trading days. We can work with that, dt time step. We also, since we're, in this case, we're going to think about time value of money, the risk-free rate of return, R, and before we had the stock goes up, the stock goes down. Let's just, the stock can go up to some value S plus, or the stock could go down to some value S minus. And we're not even say what it is. So I'm trying to make this super general. So in the end, we get a formula. We didn't use these probabilities. They didn't factor in because we hedged them away. So let's just get rid of them. All right. That's the portfolio we're going to set up, but let's write down our futures and see if we've got our two possible futures and see if we've got all the information that we need. So the stock is currently trading at S. It could go up to S plus, or it could go down to S minus. Oh, let's make an assumption then that that's true, that those S plus and S minuses are actually up and down. Oh, if I don't know what kind of option it is, how do I know what the value of this option is if the stock goes up to S plus? Well, I don't, so I'm just going to call it V plus, and if the stock happens to go down, I'm just going to call that V minus. Now maybe V minus is bigger than V plus. That's what happened last time with a put, or maybe V minus is smaller than V plus if it was a call. I don't know. We haven't specified what option it is, so we have to wait till you tell me what kind of option it is. Then I could figure out what the V plus and V minus are after I know what the S's are. Anyway, in both cases, though, of the future, our portfolio up would be V plus minus delta V minus, or if the stock goes down, V minus minus delta S minus. So those are the both cases of the future. We set those equal to each other. We got to figure out what delta is. So I'm setting both cases of the future equal and solving for delta. So the equation I get then is V plus minus delta V, or S plus, equals V minus minus delta S minus. I get delta equal to V plus minus V minus all over S plus minus S minus. Now, let's just take a second to look at that, because that looks very familiar. If I look at it as the stock's either going to go up or down. This looks like the thing I'm circling here, the V plus minus V. That's the difference in the stock, whether the stock, the difference in the option price, whether it goes up or down. So it kind of looks like the difference in the option price divided by the difference in the stock price. And I wrote the difference like slope, like derivative, on purpose. in the end, our delta, when we get all the way down to our black shoals, I'm like 3 chapters ahead of us now, but when we get there, we will not be surprised when we calculate delta to just be the derivative of our option value with respect to the stock price. It looks like a rise over run in the way we got the formula. Okay, but we'll get there later. So now I know what the delta is. And that's how many shares I should short. So our portfolio in the future, I don't have to specify which future because I've set them both the same. Once I pick this version of delta, both portfolio up, portfolio plus, and portfolio minus will be the same number. If they're the same number, I'll just arbitrarily pick the first one. V plus minus delta S plus, where I have that delta number. So as soon as I know what the S plus, V plus, S minus, V minus are, or I guess even more simply, as soon as you tell me what kind of option it is and what the S plus and S minus are, then I can figure out the V plus and V minus, then I can figure out the delta, then I can figure out the value in the future. Well, the value right now of the portfolio is V minus that delta that we already figured out times the S, the stock now. And I'm going to, we're taking time value of money into account to make a perfect formula. The amount of money that the portfolio will be worth now, I would multiply that by 1 plus R times dt. In the last video it was divided by 12, but that was because we were multiplying it by a 12, but it's R dt. I would multiply the portfolio now times the 1 plus R dt to have time value of money, to have it to grow into the value in the future. And that's going to give me then portfolio now equals 1 over 1 plus R dt portfolio future, which means the value of the option, which is what we're trying to figure out, what's V, how much should I pay for this option, is delta S plus discounted 1 plus R dt, V plus minus delta. Now, as soon as I have the what kind of option it is and what the stock price, if I have all the S's and I know what kind of option it is, then I can figure out the 2 V's. As soon as I know all the S's and the V's, I have a number for the delta. As soon as I have a number for the delta and all the S's, I can plug into this formula and figure out the value of the option, including time value of money. That's an R there, 1 plus R dt. Okay, now we're going to start to make some assumptions. We've got a formula that we could have done those other 2 examples from the previous video with. We could just plug into this and get out the value, even including time value of money. I want to be able to simplify this formula, but in order to simplify this formula, I'm going to have to start to make some assumptions. Every one of these assumptions we make then it simplifies things, but it's always a slight, it's simplification of reality, so it's not exactly right. Not exactly correct as far as it's not perfect. It's not perfect reality. But anyway, it makes the math easier. So let's do the first thing here. Let's say that this S plus is just, how do we get S plus? We take our stock price and I multiply it by some number, U for up. So the S plus I'm just replacing with SU, S times U. So like if it goes up 10%, the U would be 1.1. The same thing, I'm going to take this S minus and multiply it by D for down. So S times D would be what the value of the stock would be if it goes up, or sorry, down. So this doesn't look like it's going to help me because I had, as far as the S goes, I had S, S plus, and S minus. I had 3 variables, and now I've got S, U, and D. I still have 3 variables. but it will be a simplification later. It'll help us out later. So let's, and if I'm going to preserve this argument here, that S plus is smaller or bigger than S and S minus is smaller, then that must mean that the down number is less than 1 and the up number is greater than 1, and all these numbers should be positive. So my example was that down, like up was 1.1 if it goes up 10%, and down would be, well, later on we're going to say that that's going to be 90%, as if the percentage it goes up is always equal to the percentage it goes down. But I haven't justified that yet. So right now we're not thinking that. It's just up and down. How does that help us? Well, okay, let's get rid of stuff that we don't need. We already solved this for, we have our delta here. So I'm getting rid of stuff that was just cleaning up. So now this is going to be V plus minus V minus. Well, S plus is going to be up S minus is down S. So I can write delta as V plus minus V minus all over up minus down. I can like factor out that S on the bottom. To clean this up some more, I need to make more assumptions. Of course, every time I make an assumption, I'm simplifying the model, but that's also giving me some extra baggage. Now, I did get rid of those probabilities here, the P, the probability that it went up, and the probability that it went down. I'm going to end up bringing them back now as a general P to help me out. And I need some room, so the expected value of the stock is going to equal to the probability that it goes up times its value if it goes up, plus the probability that it goes down times the value if it goes down. That should be the expected value of what the stock is. Well, what should that be? Well, we're calling mu the drift rate of the stock, which is its drift upward, let's say, if you bought a decent stock. So that should be the expected value of the stock after one time step should be 1 plus mu dt. The drift rate is an annual, so we always say that per year, but if my time step isn't a year, I have to scale it by time. So I expect the stock to go up, multiply 1 plus mu dt times the stock value. So if the stock, the expected value of the stock then lets us cancel the S off each one. And now we have P times U plus 1 minus P times D is equal to 1 plus mu dt. This side of the equation we have numbers for. The mu I measure as the average return, annualized average return on the stock. dt we're given as the time step. If the time step's a month, then dt is a 12th. If the time step's 1 day, then dt is 1 over 252 if I'm using just trading days. So that side of the equation, the right side of the equation, I have all its numbers. The left side of the equation, the P I don't know yet, and the up and the down we're not sure of yet either. But I've got 3 unknowns on this side. Another assumption. So now not every question that we have will match this assumption, but the assumption that we're going to use is that the up is equal to 1 plus something and the down is equal to 1 minus something. that gives us, that matches this piece here. And that what that's going to do is it's going to swap out, I've got two variables here, u and d. It's going to sort of change it into only one variable. That's going to make the left side of this equation just have a p in it and just have an x in it, the two unknown variables right now. So I'm making this assumption that the stock either goes up by, if the stock goes up by 10%, then the probability, or then down, if it's up by 10%, then it's down by 10%. So at each time step, it's the two movements are linked together. So if I get a caution, because I've seen this is a mistake sometimes people make in their exercise. When they're given a question, like go back to our original, like the video before, if we're given a question in the video before the stock went up to 101 or down to 99, oh, that matches this. That makes x equal to 0.01 in the video before. But I could have just as easily set the question up saying that the stock goes up to $200 and down to $90. Now there is no x that matches both that case, so I can't use the formulas we're about to develop on that particular example. So if the up and the down match using this x formula, then I can use all the formulas that we're about to derive. So let's derive them. Putting those in for the ups and the downs. And when I do that, I end up getting that the probability is equal to 1/2 plus mu dt over 2x. Oh, some other cleanups can happen too. U minus d on the bottom, u minus d is just going to be equal to 2x. So that's going to let us clean things up on this side. I'm going to swap that u minus d out for 2x. So as soon as I figure out what x is, I can figure out my delta in terms of the stock and the x value. So I'm still working with the unknowns of probability and x. I need another equation. Two equations, two unknowns, the p and the x. Then I can get the value. And what I'm trying to do with these equations is relate real stock data to our model. So already I've used the real stock data to get the drift. That's the annual average return. That gives me the mu, so that gives me one equation with the p and the x. So I've set the expected value of the stock equal to its drift, or its like average return. The expected value of the stock is 1 plus its return. That makes good sense. What else should I do? Well, from these average returns, I could also get the annual or the scaled standard derivative or the volatility of returns. So, which is why I just write it as vol. The volatility of returns, and I can assume that the variance, that's the standard deviation of returns, scaled to be annual. So if I set the variance, so this is the stock, the actual stock variance, stock return variance. If I set that equal to the variance of our model, well, the stock either goes up or it goes down. If it goes up, then our return is u for up. That's what we multiplied the stock by. Minus the expected, the average. squared plus, oh, that happens with the probability p, we're saying. 1 minus p if it goes down, which would be down minus the average. So, and keep in mind the up I'm going to replace with 1 plus x. The down I'm going to replace with 1 minus x. So that's going to give me the sigma squared. That's the variance of the stock returns. P 1 plus x minus 1 minus mu dt squared plus 1 minus p 1 minus x minus 1 minus mu dt squared. The 1's cancel. The 1's cancel. Now there's one equation with p and x in it. There's another equation with p and x in it. Two equations, two unknowns. So all I have to do then is solve them. So, okay, but before we do that, this equation, the first equation I got by setting the expected value of the stock equal to the expected value of the stock in the next time step equal to its expected value of the stock data, the average return. I did the variance of our model equal to the actual variance. So I'm using actual stock data to get the sigmas and to get the mu's, and then I can get the probabilities and the x's as functions of the things I can get from the data, the mu's and the variance, the mu's and the sigma, let's say, volatility. So what should you do on your own? Take this value for p and sub it in for those two p's, giving me then just a value with all x's, and solve. Prove to yourself that then you get an x of sigma root dt. Well, now I know what sigma is. No, I know what x is. Then I can substitute that into this x. That means the probability that the stock goes up or down, 1 plus mu dt all over 2 sigma root dt. Oh, I got a root dt, I got a dt on the top and a root dt on the bottom. We can just cancel that to be root dt. So now I've got the p and the x. The probability that the stock goes up, the probability, and it goes up by sigma root dt. They're given by actual data. The actual stock data gives me the sigma and the mu. And I'm making the assumption here that the up and the down, when I add the up and the down, I get 0. I'm making that assumption. Let's go back. So this, we have to make sure that if I'm using this model, that the question I'm answering assumes this fact as well. But let's go back. Now I know what x is. Sigma root dt. All right, I'm going to need some space. I know what this delta is in terms of v plus and v minus here. I'm going to end up taking this delta formula, and I need to sub it into the equation that we made. I need to sub it into here and sub it into here. Oh, and this s plus, I need to turn that into s times u, and the u is 1 plus x, and the x is sigma root dt. So I need to put all these things into those things into the formula and then clean it up, do some algebra and simplify. I need some more space with that. Okay, so here's our equation that we had that we used before, and now I've got the delta in terms of the V plus, the V minus, and the S. So, our S plus, remember what our S plus was. I'm going to replace the S plus with S times U, which is S times 1 plus the X, and the X was sigma root dt. So in place of this S plus, I'm going to write this. So let's get rid of that. Oh, wait. And so we got to sub that in for the S plus and that value in for our two deltas. Let's clean up and see what we get. That's going to be V plus minus V minus all over 2 sigma root dt 1 over S times S. Oh, that's nice. That 1 over S and that S are going to cancel here. Plus time value of money piece times V plus minus our delta 1 over S, and S plus is going to be S times 1 plus sigma root dt. Again, nice, those S's cancel out. So now what do we got after these S's cancel out? Since they're canceled out, I'm just going to erase them. Gone. These are multiplied. This whole equation for the value of the option is now only a function of sigma. Where do I get sigma? That's the volatility. I get that as the annualized standard deviation of the returns. The V plus and the V minus, that's what's the value of the option if the stock goes up. V minus, what if the value of the option stock goes down. The dt, that's the time step. The R is the risk-free rate of return. That's an R. And yeah, that's it. I can just plug in those known numbers. Sigma comes from the data. The dt I decide on. The V plus and the V minus depend on what the actual option is. Plug in it all in, number, boom, there's a V. But we can do better with this equation. I mean, this equation works, but it's kind of in an ugly form. What we can do is collect upon our V pluses. So I want to write this as V equals some number times V plus some number times V minus. That's what I want to clean it up to be. Why are we doing that? Well, go back to our original idea. We figured that the value of the option should be worth some weighted average between the high value and the low value. Well, that's what these brackets are. They're the weighted average. A little bit of the high value plus a little bit of the low value. All we have to do now is do algebra and clean all this up. I'll let you do that algebra. When you do that algebra, what ends up going in this bracket is 1/2 plus R root dt over 2 sigma. And what happens in this bracket ends up being 1 minus 1/2 plus R root dt over 2 sigma. Now, that looks like our P that we got last time, except, well, not exactly. Our P that we got last time, and by not last time, back on this slide, that looks like what this is, except for instead of writing mu, I will just circle it with the mouse. Instead of writing mu, there's the R is in that place of risk-free rate of return. I guess look down here. So this is P, the probability that the stocks goes up. But this is our P prime, 1/2 plus R, risk-free rate of return, root dt all over 2 sigma. And then this second bracket ends up being 1 minus P prime. So it looks like a weighted average using probabilities. Oh, these are the risk-neutral probabilities. That P prime, that's my risk-neutral probability. We got a half in the last video, because we made r equal to 0, we ignored time value of money. So they were both, p prime would end up being a half. But if there's time value of money, then our p prime is going to be always bigger than a half. But notice there's no mu anymore. So the drift rate, the propensity for the stock to increase, is not a function, is not a factor in calculating what the value of the option is worth, which is what we got with the example of the numbers, right? If it was 90% chance going up, 10% chance of going down, it didn't make any difference. Those probabilities didn't show up. Some facts that we can consider. Remember that our portfolio was equal to V minus the number delta times the stock. And we chose delta such that the portfolio doesn't change if the stock moves up or the stock moves down. So if I differentiate this with respect to the stock, that'll be d pi ds equals dv ds minus delta's a number, ds is 1, and it's a dv ds here. And I'm setting d pi ds equal to 0. Yeah, that's how we pick the delta. We pick it so that the portfolio value doesn't change when the stock value changes. So our rate of change of portfolio with respect to stock is 0. That makes our delta equal to the rate of change of the option with respect to the stock, which is sort of what we got before when we were writing it as the difference in the value of the option divided by the difference in the value of the stock. This part looks more like a secant slope. That looks like the tangent slope, the limit of the secant slope.